Testing. How's your level?
One more time.
Hello.
Okay, good.
Looking good. All right.
Thank you.
Just let me know when you're all set with recording.
Yeah, can. Yeah, I'm
Good. Thank you.
All set?
Yeah.
All right, great. I'm going to go ahead and get started then. Hi. My name is Chris Rioux. I'm Chief Scientist and co-founder of the AppSec company in the frosty northeast Burlington, Massachusetts area. And I'm glad to be here and not there today. I actually moved out to Thousand Oaks out here, so I live out here now. And it's my first winter that's not a real winter in quite some time, so I get this all the time. So the topic for today is Unicode and problems with its implementation and common issues regarding conception and the implementation of Unicode in websites and other software. Unicode is the kind of thing that you don't want to write yourself, like the actual implementation of it. You want to be using it because everyone needs to represent international characters these days, but the actual low-level internals of Unicode are actually pretty darn hairy, and there's a lot of opportunity for them to be implemented in disparate ways, so I'm going to get into that. So Unicode, according to unicode.org, the Unicode Consortium enables people around the world to use computers in any language. Our freely available specifications and data form the foundation for software internationalization in all major operating system search engines and applications in the World Wide Web. And this quote from the New Republic I thought was great. Unicode ubiquitous to the point of being invisible. Anyone who's ever had to implement Unicode in their software knows that that is the exact opposite of the case. Generally speaking, it's an afterthought, and then once it's there, it's omnipresent. You can't seem to get around all of the little details of wrangling between representations. So it's hardly invisible. Anyway, but given the relative complexity of the internals of it, it's pretty common for people to outsource handling Unicode. They'll write everything for American English or something, and then say, oh, let's internationalize it. And ship it off to Ireland and have them do it. So many times with Unicode being an afterthought, it's not necessarily that's fun. So a little history of this, just to give you a little perspective. It's maybe repeated information for some of you, but we started off with ASCII 7-bit. This is 1 byte encoding 1 bit. It was usually reserved for parity, and it comes from the old teletypes. It's 52 years old, ASCII. But it was the first time that computers could represent the entire breadth of the English language and all of its punctuation. And they squeezed in a bunch of control characters in the front to help control the teletypes. So it's sort of an in-band control mechanism as well for the data stream. ASCII 8-bit reused that parity bit to create an extra bank of 128 characters and basically swap out that top bank for various what we call code pages. You could put in a Russian code page or a Greek one and represent characters from those different languages. This worked fine, except you can see here you had a bunch of different code pages. You had some international attempts at standardization. You had some that showed up just out of like PC-DOS. You had some that showed up in Windows. And there's probably hundreds and hundreds of encodings, different ways to interpret those top 128 characters. So Unicode came along because so many code pages existed that things had to be basically recoded every time for every different language, rather than using the same compilation, just having a string table which you could then swap out. It became very operating system dependent how your program is interpreted. also character sets that included, more than 256 characters or 128 characters had really no hope of being represented reasonably. The interim fix there was double byte character sets. So rather than using straight ASCII, it would conform to ASCII conventions, but interpret the 2 bytes in the sequence as being a certain character and displaying that. So this is really the first time that character composition, the notion of composition, shows up with code points representing a single character. So you have 2 code points that come together to form one character. The emergence of Mojibake. Mojibake is slang for what happens when you decide to interpret something in the wrong code page. You have double weight character sets where you have maybe some Chinese phrase, and you interpret it as ASCII, and all of a sudden it's like, oh, this is garbage, because you really don't have a way of determining from the byte stream itself what code page should be used to interpret it. There's no obvious way to do that. So sometimes even today you get web pages and things that have garbage in them because they're being trained right. So the word for that is Mojibake. I'm probably mispronouncing that. Might be some Japanese pronunciation. So yeah, basically in 1991, consortium developed by Apple and Xerox released the first draft of the Unicode standard, which is an attempt to unify all of these character sets into one place and have one universal way of representing everything. And it was really important that this happened at around the same time as the internet became a thing, because rather than having discrete systems that could each be on their own code page and their own keyboards and everything else, you now have these things talking to each other, and you had to have a way of getting them to agree on what one thing meant across the internet. So having a common alphabet for the entire world became the sort of much of a problem that Unicode tried to solve. So let's talk about it a little bit, what it defines exactly. The first thing that becomes obvious is that we stop talking about bytes so much and we start talking more about code points. Code point is a series of bytes, or a group of bytes, that defines the index into a table of Unicode code points. Code points may or may not represent a character, but they are locations in a table. That's all it is, really. It's an index into a giant table of Unicode stuff. Character is a series of code points. It could be one code point, many characters are, but a character in various languages, like E with an accent mark, what is that? It's E and an accent mark put together to form E and an accent mark. Or it's them separately but interpreted the same way. So you really, what we're thinking about here is the whole notion of composition. You could look at some of the stranger languages out there, like Thai, where there are combining characters that come together to form a single character. So you have 3 characters, or 1 character that has a whole bunch of extra code points represented. So a single character can have a practically infinite length in terms of code points. So now you're starting to see that there's the interpretation length is different depending on what sort of level you're looking at. Length of bytes, length of code points, and length of character string are all different things in Unicode. So the goal is to represent all the different scripts, all the different human scripts that we use, including Unicode actually supports uniform and Egyptian hieroglyphics. All the different characters from all the past languages that we've ever been interested in. Now, some of those languages are excluded in certain, Old Norse or something has, there's certain characters that might not be in the Unicode set. Some medieval languages are not there. And science fiction languages like Tengwar and Klingon are not represented in Unicode set. Though there are some people very actively pushing for their inclusion. So don't be surprised at some point if there's a, high elven, Unicode code page at some point. Anyway, so the question now is, once you have this table of code points, how do you then represent it as bytes? Everyone talks bytes. So you need to represent millions of characters. If you have 2 bytes alone, you can do 64K characters. 3 bytes, 216 characters. 4 bytes, and to the power of 32 characters. So the desire to remain compatible with ASCII, because nothing just moves from one standard to another without having some kind of transition, led us to an 8-bit UTF-8 representation. It's Unicode transformation format. UCS means Universal Character Set. UCS is sort of like a deprecated subset of UTF. So if you see UCS2 being used, that's actually UTF-16, but it's a subset of it. So these days we talk UTF, not UCS. Sorry? Well, even though you refer to it as UTF-16, but the older standards for, like, say, if you look at old PDF files describing, say, the NTFS file format and the old Win32 docs, they'll say things like UCS2, but the newer versions of things will have moved on to UTF-16. Anyway, so there are popular variants of UTF, UTF-8, UTF-16, UTF-32, that encode the code points using different numbers of points. So let's talk UTF-32 first. Basically, a code unit is the same size as a code point, which is 4 bytes. Basically fixed width for everything. And it's generally viewed as overkill. Some people say that's slow, or something like that. It's hardly a problem for computers these days to handle strings that are encoded with UTF-32. So don't worry about it being slow. Worry about it being a little bit overkill, and the fact that it can represent code points that aren't actually Unicode. Unicode actually only has code points from 0.0 through 10FFFF. That's the Unicode range. Now it can represent all, 0 through all Fs. That's a lot more characters, but those are not necessarily actually mapped to anything in Unicode land. It's kind of reserved for expansion. But that means you can make a UTF-32 character that has no actual renderability. It would be illegal to make it 0020000. That wouldn't actually have representation. So anyway, UTF-32, the HTML5 spec suggests against using it for anything. So you'll be seeing a lot more of the other encodings in this one, but internally, in certain compiler representations, like GCC, for example, it became standard. UTF-8 is probably the most popular format. It's actually 86.4% of web pages, various file systems, including BFAT and DXT2FS. It has some interesting properties. The idea here is that the code unit is 8 bits. And that for the first 127 characters, it looks exactly like ASCII. So UTF-8 can be interpreted like ASCII, but can also encode things that are not ASCII. It has certain properties, like it's self-synchronizing. Self-synchronizing basically means you can plop down anywhere in the stream and figure out where, just by walking forward, where you are in terms of if you're inside a character or if you're at the beginning of a character. The notion of a continuation shows up here, where you have certain bytes that are valid starts of a character, and then other bytes that are valid continuations of that previous block. Where the first byte will actually code how many continuation bytes are expected. So that way you know exactly sort of where you are on the string. It's not possible to interpret a Unicode string by dropping yourself down in the middle. You can't just interpret it differently. You have to find that start byte, and then you can go through the continuation bytes. So it solves that problem. It has, just luckily it has the same byte sorting as a lexicographic code point sort. In other words, the byte order, the sorting that you perform keeps everything in the same order as the Unicode code page bytes. So your sort's going to necessarily have to be different from each other. Now, there's a whole series of different things about what sorting even means. We'll get into that. So anyway, UTF-8 does have some problems. Not all sequences of bytes are valid UTF-8. Too many continuation bytes can exist, not enough continuation bytes. Overlong encodings, so you can have 4 bytes in UTF-8 that actually represent something that could be represented with 3 bytes in UTF-8. So it's possible to use more bytes than necessary to represent the same thing. That means the same character. There's multiple UTF-8 representations. That means if you're building filters, trying to filter a string or a path based on a series of UTF-8 bytes, you can probably get fooled because somebody could just use a 4-byte encoding for a character instead of a 3-byte character, and you will be missing out on that. So in order to deal with that, you have to normalize the string and remove all these multiple encodings and make it a sort of canonicalized representation. That in itself adds a whole series of other problems that we'll talk about too. So you can use a 4-byte sequence that decodes through a value greater than the maximum size, the maximum number for Unicode code form as well. So there's all kinds of ways to make UTF-8 string that aren't valid at all. Valid sequences, I'm not going to get into this too much, but basically there are ways, some of these encodings, if you read the slides that I'm reading right there, basically there's ways to make UTF-8 strings that are not considered valid Unicode. So it's important that whatever you're doing in parsing has some kind of validation as well as interpretation. UTF-16 is pretty common. It's the second most common way of representing Unicode. 16-bit words can be big endian or little endian because of that. And there's a solution for representing that called a byte order hard. Is it FFFE or FE, depending if it's big or little endian. Those characters, FF and FE, are not used for anything else in Unicode. In the representation, so if you run into that, you know it's a byte order. You find that out of all those other combinations. And internally, it is used by Windows, .NET, Qt, Symbian, Joliet, the ISO extended CD-ROM file system, HFS Plus for Mac. Even though a lot of Objective-C and things are UTF-8 internally, the actual file system is UTF-16. So you know there always have to be a conversion between UTF-8 and UTF-16 for this to work. Half the web is UTF-8, NTFS, and Windows is UTF-16. You know there's going to be a conversion going on. So we can leverage that in terms of messing with things. The UTF-16 gets around by using this concept called a surrogate pair, which is 2 UTF code points put together in this particular shape, a particular bit pattern that says I'm a surrogate pair, and combined together can represent things within that Unicode range from 0 through 10 FFFF. So anyway, there are other non-standard formats that you probably won't run into, but you might have read about UTF-7, which is a 7-bit version of UTF-8, typically. UTF-1, which is an older version of UTF-8. UTF-AppSec, which is meant to represent like the first 127, 128 characters using the AppSec encoding rather than ASCII code. And then there's some sort of joke UTFs, UTF-9 and UTF-18, which are actually April Fool's Day RFCs. If you're looking for an entertaining read about Unicode, check out those RFC 4042. It's not quite as bad as TCP tunnel over carrier pigeon, but it's up there. So Unicode has a lot of objects. There's a lot of character combinations and things that have to be interpreted in a special way. If you look at the ICU, C++/Java Unicode parsing library, it is exceptionally big for what it does. It has to handle all of these crazy combinations of characters. You have specials, which are basically, I'll explain that in a minute, but you have specials by order marks, combining characters, combining grapheme joiners, Unicode control characters, duplicate characters, glyph variants, figure spaces, regional indicator symbols, and you also have a range of private use characters which can be represented any way
without having a sort of standard representation. Special characters include things like the interlinear annotation anchor, the annotation separator, and annotation terminator. It allows Unicode, the concept of Unicode string, to have embedded annotations, like rich text. So it actually defines like a rich text system, which is a little bit crazy. It has an object replacement character, which is used for can be used for compound document insertion, depending on, I mean, this is all, think about ASCII, it's just letters. These control characters are kind of nuts because it's more than just like terminal control. It implies control flow in programming. It's going to do a different thing if you pass in an object replacement character sometimes. Now, many of these things are not implemented in a lot of implementations of Unicode parsing, but Unicode 7, it's pretty much mandating that a lot of these things get implemented. So you can start seeing more and more of these show up. Byte order mark, again, looks like FEFF. But in UTF-8, it does not look that way. In fact, you don't really usually see byte order marks in UTF-8 because it's optional. There's really no need to do byte order mark in UTF-8 because it's all bytes anyway. But there's a way of representing it. If you see EF, BB, BF, that's actually the FEFF code point in UTF-8. It's valid, but not necessary. So the same string in UTF-16 could have, again, two different UTF-8 representations, one without byte order mark. UTF-32 also has it, again, rarely used. So certain characters are also glyph variants. Basically, you've probably seen some spoofing attacks where say the Greek O, Omicron, was used in place of the Latin O. It was kind of a big deal that led to a whole standard around DNS naming for international DNS names, so that people could register yahoo.com with the two O's being Cyrillic or Greek. The string you see here, one of those characters is Cyrillic. It's like, it looks the same. It's because it's actually represented exactly the same way. Now, if I were to change the font there, you actually might notice that it does look different in some fonts, but just about every normal script, it's going to look exactly the same. This is an error, this one here, error C2146 that I got from Microsoft Visual Studio running a C++ compilation. It's a syntax error, missing semicolon before identifier semicolon. Since when is an identifier, a semicolon an identifier in C? It's not. That's because that's not a semicolon. I pasted that into somebody's program, and it takes you a while to figure out that it's actually a Greek question mark, and not the semicolon. So you can spend a long time debugging that, being like, what the hell is my compiler? Before you realize what you're looking at is not, in fact, a semicolon at all. So the question came up, what else can you screw up with Unicode? Right? So, I'm looking at the Unicode control characters, and so these are basically mapped the original sort of ASCII control characters. Nothing really that interesting there, but just note that there's a code point that represents all these ASCII control codes, but it's different than the low code point where they actually have a separate high range that represents the same character twice. So you have two CRLFs. That means there's a second line feed in Unicode and line separator to 2028 and paragraph separator like 2029. Those have to be interpreted at some point if you're going to be parsing a file into lines. You might, in one way of looking at it, might say, it's got two lines, but it has this line separator in the middle, and then another piece of code can look at the same thing and say it's two lines instead of one. So there's some issues there. Combining character sequence and graphing joiners basically are code points that are merged together to form characters that are combined. As clear as I can make it. So let's just go into some of these Unicode operations and implementations in various languages. I'm going to pick on a particular telltale function, which is just string length. There are many types of operations. out there. Normalization, which is making the byte stream, eliminating all of the potential ways of representing a bunch of code points using various byte streams. The things like string length, how strings are terminated, how things are compared, how they're collated, how we sort Unicode strings. Is there a uniform way of like, sorting the Cyrillic O from an English O? What's the right way to do that? Case conversion. Is there an uppercase version of a particular character that happens to look like the English O and that kind of thing? So normalization I'm not going to get into too much, but just know that there's a bunch of different ways, composition and decomposition, the two primary operators here, that will take characters and either make the E with an exit mark one thing or make them two things. So deciding on a particular normalization format is kind of a prerequisite to being able to pick which of these operations are actually going to be performing. Code units are typically how we think about measuring the length of the string. So in UTF-8, we tend to think in code units of 1 byte. In UTF-16, 2 bytes, and UTF-13, 4 bytes. But the number of characters in the string, as represented, let's say, in web browsers, password field. The number of characters, you say you want 8 character long passwords. Or is that 8 Unicode characters or 8 code points? Depends on how you're looking at it. What about usernames where somebody is logging in on, with a name with like an accent mark in the name, but on a completely different keyboard might be keying in the same username, but get a different Unicode character. You want it to sort of work for them. So the question is, do you normalize usernames or not? Or are the risks around that? So again, I have some recommendations for this, but we're going to get to the actual problems that I've seen out there. So yeah, you could look at character length. You could look at combined characters. You could look at you could look at straight bytes, characters. There's a bunch of different ways of looking at it. Case conversion is a little tricky. In C, the operation of a C program is not well defined in the case of Unicode. If you were to write a piece of code and then change the locale environment variable in the shell that runs the program, it will change how things like the standard library's lexicographical compare works. So it could produce a really different sort order and different interpretation of the strings of the program. So yeah, for in this little program down here, you can see as a uppercase string and a lowercase string, and comparing them. If you set here the locale to be a different locale than LCU or whatever it is, it's the US locale. You can get this to either say that one is less than the other or one is greater than the other, depending. And the code doesn't change, it's just that external environment variable. So LC all is you set it in Germany, and it interprets a different one. S1 is less than S2 in the US, and it's not in German locale. So I looked at a bunch of compilers and a bunch of languages and said, well, how do they represent Unicode strings, and how can we mess with the implementation a little bit and get it to do anything that it's not supposed to do? So I looked at GCC, MSVC on Windows, Projector C, and I'm playing C++ 11 in some contexts, Python, Ruby, and a few other things, just to see how they would handle the same inputs. The question now is, how do you represent literals in those things? And there's some examples here. Everybody tends to view the literals a little differently, but the idea of representing code points is sort of universal. The syntax is going to be different. So you can see here in the URL, it can be different than XML versus CSS versus Ruby and Perl. They all have slightly different representations of the same concept. But we can universally talk about code points, regardless of the lexical literal representation of those things. So let's look at GCC. Backslash U 001011083 is a code point that is in the upper range of what Unicode is can represent. And I print out the wide character string length of that string and the size of the W char key that it's made up of. So on GCC Linux, playing OS X, you run the program and it says that the length of the string is 1, which it would be making sense if it was UTF-32, which is it's 1 unit, 1 code unit being displayed here, and 4 byte wide character. So that's basically informational. In MSVC, I run the same thing. And it says that the length of the character, or the character string, that same high code point, is actually of length 2. So 2 code units are involved in this. And the size of a particular code unit, the W char key, is length 2. So you can tell that the internal representation there is UTF-16. Now, in C++ and C and MSVC, you can have Unicode in the identifiers in the program. So you can see there, I put some exceptionally long, ugly characters in this name of function compiled to. So you can have some pretty interesting looking code in Visual Studio now. This also works in C#. So you can have Japanese characters, Chinese characters, whatever, as the names of functions and variables. It makes pretty interesting text. As a complete sidebar, if anyone's actually interested in messing around with the compiler for Visual Studio, one thing I tried a while back that still works today is you can pound include UNC paths. So you can say pound include // IP address /foo.h and have that be dynamically generated by some computer across the internet. Every time someone compiles a program, it's going to come up differently. And the compiler actually makes the network call, does all the authentication outbound. If you were to go ahead and implement a pass the hash type setup where somebody was compiling, you'd have developers with developer credentials making outbound SMB connections to an arbitrary IP of your choice. That's just a little fun. So nothing to do with Unicode. So anyway, you can see that there were Unicode literals in the actual source code for Visual Studio. It's also supported by GCC. The question is, how does it represent those things in compiler representation? If I took this funky Unicode here and said size of that, in MSVC, the character size for that is 1. The string size for that same thing is 2. In GCC, the character size is 4. But you think of it in UTF-32, it's actually because that character is being extended to an int before the size is taken. But the size of the same character as a string is like 3. Fascinating. So what is the length of that? How do you interpret that? That's the actual effective size required by UTF-8 to represent that character. What if GCC was UTF-32? How do you even get that? That's a good question. So, Objective-C. If you were to take the Earth globe emoji and ask for the length using the length function on an S string, you get length 2. Okay? If you ask for the length using length of bytes using encoding, say you see, convert it to UTF-32, and then divide by 4, which is the length of the code points, the code units in UTF-4, you get the length is actually 1. So it's actually 1 character. And if you were to ask for, let's say, a pre-composed character, E with an accent mark, directly with length, you would get 2, because it's actually 2 E and accent mark. And if you put it together using pre-composed string with canonical mapping, like if you're canonicalizing a username, you would get length of 1. So we have a bunch of different ways of getting, these different lengths. Python and Ruby and other interpreted languages are actually very fun starts. A null character in Python is length 1. It's going to be 1 character is length 1 as well, as you expect. a 10,000 character, it's like 2. What does that tell us about Python's internal representation? That is UTF-16. Because that character could only be represented using 2 surrogate pairs. We'll use a surrogate pair to show it. So you can see that if you to take the character, do an index on it, you actually get the 2 surrogate pairs. You put index 0 and you get DBC4, and index 1 you get DCA3. That shows the internal representation right there. If you were to, again, that's the same thing. If you were to encode that though with UTF-8, now you get like 4, because it's actually representing it 4 bytes in an ASCII type string. That's not completely out of whack, but what about UTF-16? It was internally UTF-16, but if you ask it to encode it as UTF-16, it shows up as being 6 bytes long. What's going on here, right? That adds implicitly the byte order mark that wasn't there the first time. So internally, it doesn't need the byte order mark, but as soon as it makes it external, it grows by 2 characters so that it can add it. A little tricky. Let's look at root. So we have 2 code points here representing 2 squiggly little characters. And we encode it with UTF-8, and we get something that's length 2. That's fine. That tells us internally that it's UTF-8. So if we encode with UTF-16 and UTF-32, what do we get? Well, you can see the byte order mark being prepended, followed by those 2 characters. So it's internally representing it on the screen. It's externally representing it with code points on the screen, regardless of whatever the actual internal representation is. When it prints it out, what you're seeing is the same thing, regardless of whether it's UTF-16 or 32. Even though it looks exactly the same on the screen, if you ask for the length of these things, one is length 6 and one is length 12. Despite the fact that when you look at it right here, this right here, is exactly the same shot. So you can't even tell what you're looking at when you're looking at it. Let's take some code pairs that are surrogate pairs and a little bit higher up in the list of possible code points. This, once evaluated, DBC4, DCA3, gives you a UTF-8 internal representation. Again, we know where UTF-8 internally, so this isn't that surprising, other than the fact that if you just replace those with 1000, it actually shows you the character instead. So what's going on here? Let's say we encode that as UTF-16. What do you think the result is? That's right, invalid byte sequence error. There you go, read. That's something, right? So apparently, something that is representable in UTF-8 in Ruby cannot be represented easily in UTF-16 if it's code point like that. So you can end up throwing an exception in certain cases. Regular expressions exist in Unicode. I'm recommending that you don't do it and that you do something else completely. Switching careers might be a good idea if this is something that comes up. The notion of having new lines and different ways of representing characters, the whole notion of Graphian cluster mashing is kind of a big mess. It's doable, but if you're investigating regular expressions from Unicode, you might think twice and be exceptionally careful about how you do it. Because all those crazy rules about whether characters are the same, you have to know the lingo to be able to choose exactly what regular expression does what you intend it to do. So let's talk about security. Security in Unicode are not obvious in terms, this is why I chose the topic. It's not clear necessarily where the security ramifications of Unicode are. You can think of a few things right off the top of your head probably, but it turns out that Unicode implementations being hardly consistent is problem number one. That you don't want to write your own Unicode. It's like writing your own crypto. Don't do it unless it's all you intend to do. It's the kind of thing that you're not going to get it right if you're just doing it half-assed. Use somebody else's library, unless, like writing your own crypto, don't do it to solve a problem. Do it to write the best crypto ever. Do the same kind of thing with Unicode. Don't write your own Unicode. Converting back and forth between UTF-8 and UTF-16 happens so frequently that if people don't do it exactly right, you end up with a telephone game on the other end. So encoding is like the internals of Windows NT, where UTF-16 is all over the place, but then they use a counted length to represent the length of the Unicode string. Is a little tricky because you can only interpret that as the number of code units. So again, Windows kernels and iOS both use Unicode kernel. So there's a fallow field there of opportunities to screw with things. Well-known issues. Not going to get into these with too much detail because there's plenty of examples out there. Buffer overflows, path canonizations, URL and WAF filter bypasses, character spoofing are all things that you've probably seen that are basically Unicode's fault. I'm just going to get into some other stuff, but I'll give you one example of the username and canonicalization thing I alluded to before. Spotify Labs had an issue a while back. You could do the following. You find a user account to hijack. For example, let's hijack the account belonging to user Big Bird. You can create a new Spotify account with username Big Bird using Unicode characters that happen to look just like Big Bird and be lexicographically normalized to Big Bird. So you would create the account using the Unicode name and then request a password reset for your account. The password reset link would be sent to the email you registered for your account, and then you would change the password, and now that would actually change it for the original Big Bird account that had the normalized representation. So then you could log in as Big Bird instead. And so there are some risks there. In the desire to handle uniform, Unicode login names. There's the risk that you may create a collision where two different inputs represent the same username. It was a legit thing that happened out there. Cortex exploit was a series of Arabic characters, which really had no meaning specifically, that gave Cortex framework a really hard time in objective-C. You could send it to somebody over SMS, you could use iMessage, you could have a web page, or even the name of a Wi-Fi network that was the string, and it would cause a kernel crash on iOS devices. This was sort of a fun little thing to do. To me, it was the equivalent of pinging somebody on the internet back in 1992 with +++ATH0 as the body of the ping, so they'd send it back to you and knock them offline. This kind of thing is the same level of mischief. It's not necessarily going to be an exploitable thing, but it can be a giant pain in the butt. Apple had to fix that. So I decided to start messing around with the combined character sequence and stuff. You see this sometimes as people make these Unicode, sort of garbage in like Twitter posts and things. You can see characters all over the place. Sorry? Yeah, Zelda text. Yeah, that mess is usually the result of people messing with combining characters. So the combining character class, an example of that is E0B894, which is the type character DilDog. If you replace after that the type character Maitaku, E0B987, you can see that it actually sort of stacks one character up on top of the next one. So it represents one character, but it uses two. Now, if you were to put a bunch of the Maitakus after the DilDog, you would end up with one character that has a long string of garbage, like that. You can see even PowerPoint doesn't like it that much. So x plus y times 256, that's 256 of those little Maitakus stuck to the top there. So I decided, given the fact that that's a one character thing, by normalized rules, I decided to start pasting that into everything on the internet and seeing what it did. So fun with Unicode. Fun with Dig. Start with Dig. Good candidate here is to paste it into search boxes. You're going to have some kind of length validator, but it's usually character length based. So you can sweep this giant thing into something that's only meant to handle client-side security with just 2 characters, 10 characters, 16 characters. Well, giant turd is one character. You can squeeze it into a lot of places. Paste that in the search box, and I get a couple hundred. We're getting reports this page cannot be found, etc. Same thing with Twitter. Paste that in Twitter search box. Something is technically wrong. You get another server-side crash. And various other places cramming it in there. Pull off stuff like this. the web page is not available. Decided to start messing with Dropbox. Dropbox URLs have fields for what Dropbox and what file name, things like that. And you can make 500 type in there too. See those DilDogs all in the URL there. After I realized that this was actually a server-side thing, it's going to be 500. It's actually crashing some Apache off in space, right? I figured I might as well eat my own dog food and try my own website, Unicodes.com. And sure enough, search box temporarily unavailable. At that point, I was wondering, okay, what is actually happening? Is this going to result in something exploitable? And so I popped open Charles proxy to take a look at what was coming back, and it was in fact giving a 503 service temporarily unavailable. To me, this started to make me think, that proxies and load balancers are going to be having a hard time with this. I continued to feed it into Bing. I got a location that you search for, nice big long string of DilDogs. And that side doesn't look too problematic, but you can see that as it searches for it, it says just a moment. And it's going to sit there for a long time before it eventually returns with driving directions are temporarily unavailable, please try again. That's not the typical error it gives you when a place name is not found. It usually returns very quickly as soon as the place name is found. You're causing something to crap out on the back end of big maps and do that. iTunes. This is some Apple stuff. If you take the ID field for an app like Angry Birds, and you paste the DilDogs in there, you get your request appears from error and no response. Again, on the back end of that, in Charles Proxy, we look at it, it's giving the 500 internal server error. So you know that again, it's crashing something off its bed. See here, also backdate that. Spelling evaluations too. In Google, this is where it started to get fun. I decided, Google has a lot of different apps, Google Drive, Gmail, all this other stuff like this. So let's see how well I handle Unicode. As soon as I popped this in, I was actually looking at Alexa, and that's when Google Chrome crashed on me. And the history didn't handle what I was putting on. So Chrome took it off. So then I made a Google Doc. I named it DilDogs. And by itself, that seemed reasonable. I decided to send it to myself via Gmail. That's what it looked like. Okay. There you go. You want to view that? You get that in your email and like, view as Google Doc. That's like, okay, well, good idea. What happens when you view it as a Google Doc? Right? You get, this thing opened up. You can see, the garbage name, garbage in the cell there. The first thing that happened when I opened that up was Google, the JavaScript implementation took it down. And just sat there forever. So yeah, as soon as I went back to look at the thing, I get Google telling me, we're sorry, abuse tags. I have no idea what that means, some kind of strange internal error, right? But yeah, Google Drive is pissed. It says abuse tags. We're sorry for the inconvenience. And by the time you actually do get into it, it says, let's say I created another document here. I was trying to save it. And it says an error has occurred, cannot save your changes. Google Drive encountered an error. You can see here, I'm now actually trying to delete that document out of my Google Drive because I just crapped out my Google Drive, right? So I'm trying to get rid of the document, and now it says the server encountered an error. Please try again later. As I try to get rid of it, and it won't go away. And then it says no connection detected. And then it says the app is currently unreachable. At this point, I was unable to reach Google Drive from a different computer as well. The entire Google Drive thing that I was attached to just totally bumped over, and Google Drive was gone for a span of about 30 seconds anyway. So, just a character in the name of something, right? Now, mind you, this is Google Drive, so you're running the client, it synchronizes that Go deck to the hard drive. So now you have a file on your disk that's named that big, ugly Unicode thing. So I try to delete it from there instead. And Windows says destination path too long, file names would be too long for the destination folder. It really doesn't matter how long it is, it just can't seem to get rid of the damn thing. Even if you aren't sending it to the cycle bin, you try to delete it directly or use the command line to do it, it won't go away. So now you've got this stupid file that just won't disappear from your file system. If you share it out to somebody else and they accept it, it'll put it on their file system and they can't delete it either. Okay? So the only way I was able to get rid of it eventually was to rename it and then delete it. If you try to delete it, it won't work, but you can rename it and then delete it. So, and then we get away with that. Anyway, that's pretty much going to wrap this up. Again, it's pretty clear that, just idly pasting a bunch of Unicode characters into websites, isn't necessarily going to cause any major harm, but it can give you an idea of general code quality, and it can give you some ideas around where to attack next. There's opportunities to slip by filters all over the place, and the conversions between UTF-8 and UTF-16 are often going to cause problems for implementers. So, recommendations, go with UTF-8 everywhere possible. We're already mostly there anyway. Of course, you can't help it when the operating system you're using is not using UTF-8 code. It's nothing you can get around. But when you write your own code, you have a choice to make. And if you can choose UTF-8, you'll probably do the right thing. For more detail on that, visit the website utf8everywhere.org. It has more, like a whole other hour's worth of conversation about why you should choose it. I recommend these various links at the end here, and of course the Wikipedia page for Unicode. I'm willing to take any questions, but that's basically the end of it for now. Go ahead.
There's a vulnerability recently GitHub material and involved around ignored code points. Symbols and sounds.
Basically, there are code points in Unicode that have no way of being parsed. They're not legitimate valid code points. I would imagine that if they're having Unicode translation issues, that a big deal for them would be overlong character code points as well. So, yeah, there are characters that you can't represent in different code. As a result, you maybe would be able to check in something with a comment that has some interesting stuff in it, and then when it's parsed out upon Git pull or some sort, you see it on the screen, and it tries to show the result. At that point, you're crashing some Unicode choker. That way, people can't, do a Git pull. So it may be possible to, again, like in the example of Google Drive flag, you can create a file that's named some terrible stuff, and then people happen to get it and can't delete it, or can't manipulate it, or can't edit it, can't rename it, or whatever it is. It can cause, at least the service or severe runs. So, like that.
Do you consider any cases where Unicode could help with something like cross-site scripting, where you browse with interpret characters?
Oh yeah, sure. Generally speaking, any kind of WAF filtering. If there's normalization involved, it's going to be a problem. There's more than one way of representing a thing. The notion of a new line, if there's UTF-8 sensitive code, many times there's things like log injections and CRLF injection that will bug class CRLF injections totally differently. CR and LF are different. Maybe there's multiple CRs and multiple LFs. It's like, are you actually looking for the Unicode one too, or not? So yeah, spoofing is a huge problem. Okay, that's it. All right, thanks guys.